In this presentation, we're going to have a look at what electrode potentials are, how they're measured using the standard hydrogen electrode, and a little bit at the standard representation and notation that we can use to show electrode potentials. We're going to start off looking at electrode potentials, and what I've drawn here is a copper strip in a beaker surrounded by copper sulfate solution. So we'll label that up. Now, what happens when I put a copper strip into a solution of copper sulfate? Now, to you or I, it looks like nothing happens, but it actually forms a dynamic equilibrium. If you remember, the whole thing with dynamic equilibrium is that it's moving, continuously moving, but you can't see it's moving because it's in equilibrium. So the concentrations of the left and the right hand side appear not to be changing, but they are moving continuously. Now, the dynamic equilibrium that forms, we've got the copper ions in the copper sulfate solution. So they are copper 2 plus, and they are gaining, they can be gaining 2 electrons, and they can be turning into copper, solid copper. But equally, at the same time, the solid copper can be turning back into copper 2 plus ions and 2 electrons. Now, we don't have to use copper and copper 2 plus for this. I've used it because it's a familiar example to you, but we can use any metal. If I just use an M to show any metal, and any metal can gain, or any metal with an N plus charge can gain N number of electrons and turn into the metal. So any metal ion with an N plus charge can gain N number of electrons and form an equilibrium with the metal. So we can do this many different ways with different metals. Now, if our equilibrium lies on the left-hand side, what does that mean? So if you've got an equilibrium that lies on the left-hand side, it's going to favour being in the ionized form, so in the copper 2 plus form. So if it lies on the left, it's going to be negatively charged because it's going to have excess electrons. So if it lies on the left, then it's going to be a negative electrode. And if it lies on the right hand side, then it will actually form a positive electrode because it's going to have lost electrons. Right, so we would have the positive. Now, as you know, some metals are more reactive than others. Some metals are better at losing electrons than others, and some metals are better at gaining electrons than others. It depends on whether they are good oxidizing agents or whether they're good reducing agents. So, for example, metals in group 1, so something like potassium. Okay, potassium very much favours, so we're going to draw the equation for this, but potassium, the position of the equilibrium is going to lie very, very much on the left-hand side because potassium favours losing electrons. So if it were possible to make an electrode out of potassium in a solution of potassium ions, which quite frankly it isn't because the potassium would explode when you put it into an aqueous solution, but if it were possible, the position of its electrode would lie very, very much on the left-hand side. Okay, so it would lie on the left, and it would be a very negative electrode. Now, these are not the only electrodes or half cells we can make. We can also make redox electrodes where we don't have a piece of metal in a solution, but instead we can have an inert electrode and this inert electrode is dipped into a solution with a mixture of ions. So in here we could have, and it's a bit of a murky colour because we've got a mixture of Fe2 plus aqueous and Fe3 plus aqueous. One of which is kind of a green colour, one of which is a brown colour, so I've made it a murky brown. So our half equation this time would be the Fe3 plus gaining one electron and forming an equilibrium with Fe2 plus. And we use an inert electrode, so this time you can use graphite, but graphite would work fine. If you want to use something more expensive, you could use, say, platinum. Now, there's a very special type of extra electrode using gases, and I'm going to show you that using the standard hydrogen electrode. Now, this is the standard hydrogen electrode. It's the most common one that you're likely to see where there's gases being used, but this is the standard setup you'd have for gases. So we have 1 atmosphere pressure hydrogen gas, and that gas is pumped in through a special glass tube, and the special glass tube has got little holes at the bottom, which let any bubbles of hydrogen escape. You'll see then we've got a platinum electrode, and the platinum electrode is inert, and that will connect us up to the voltmeter. And then we have an acid solution, and our acid solution contains 1 molar hydrogen ions. So again, like with the other electrodes, you've got to have 1 molar solution of ions, but because we can't use solid hydrogen as our electrode, what we do is we use hydrogen gas and we pump it in, and that gas goes next to the platinum electrode. Now, the standard hydrogen electrode is very, very important. It is used as the standard against which we measure everything else. So the standard hydrogen electrode is called a standard because we use it as the standard against which everything else is measured. Now, the equation for it would be, so we've got hydrogen ions and they're gaining an electron, and we form an equilibrium making hydrogen gas, so we're going to need 2 hydrogen ions and 2 electrons. Now, this is particularly important because at 298K, and that's another important thing I need to point out on here, so at 298K and 1 atmosphere pressure, now let's remind ourselves 1 atmosphere pressure is also 100 kilopascals, so you might see it written as both. So at 298K, 1 atmosphere pressure, our standard hydrogen electrode, which is our reference, it's a primary standard, is given an electropotential of 0.00 volts. So what does that mean? Well, it means that in those particular conditions, our equilibrium lies exactly in the middle. We're not moving to the left, we're not moving to the right, so our equilibrium is exactly in the middle with equal concentrations of hydrogen and hydrogen ions. So it's not slightly negative, it's not slightly positive, it's exactly 0. Now the forwards reaction has a delta H is negative, which means it's exothermic. So if we change the temperature, if we use our understanding of equilibrium, so if we increase the temperature, we're going to push the equilibrium to the endothermic side. So we would push it to the left and we would make our electrode more negative. If we were to decrease the temperature, we're going to push the equilibrium to the right and we would make it more positive. If we were to change the pressure, we've got 1 mole of gas on the right hand side, we don't have any moles of gas on the left hand side, so if we increase the pressure we're going to move it to the left hand side where there are 0 moles of gas, and we would get a more negative electrode. So the conditions on the standard hydrogen electrode are particularly important because they maintain this very important 0 0.00 volts, which is the standard, the primary standard against which we measure other things. So if we want to measure an electrode potential, the easiest way to do it would be to set up your half cell alongside a standard hydrogen electrode. And what you would then do is, using crocodile clips, you would connect up both lots of cells would be connected up to a voltmeter to measure the potential difference. So this would be a high resistance voltmeter. So we connect it up to measure the potential difference. Now at the moment we've got our electrons are able to move, but the ions cannot move, and the ions need to be able to move for the circuit to be complete. So the thing that's missing from this is very important. We would have something that would use to join the two beakers together, and this would be called a salt bridge. And the salt bridge in its simplest form is just a piece of filter paper soaked in potassium nitrate. So this is how we would measure a simple half cell. I could replace the copper half cell, the copper 2 plus half cell, with the Fe2 plus Fe3 plus half cell, or with a zinc half cell. But if we put our primary standard, the standard hydrogen electrode, on the left-hand side, and then we measure the other other half cell, the other electrode, then we would be able to see whether it was positive or negative and get a value for it as measured compared to the standard hydrogen electrode. Now, most of the time, you don't have a standard hydrogen electrode. Most of the time, we don't have one in college, so we're not able to pump hydrogen gas through a special cylinder with bubbles coming out. So most of the time, what you would do is measure one half cell against another half cell. So I would compare the copper cell to the zinc cell, and then by using the measurements I made, I'd be able to work out what the difference was between them and work out what the actual half cells would be. So one final point on this, the half cell, what I would actually measure with what I've got set up here. So if our hydrogen electrode is 0, the copper would be measured, the copper 2 plus electrode would be given a value of plus 0.34 volts. So what does that mean? Well, if we write the equation always as the gaining electrons, so if it's a positive electrode potential, it means that it lies more on the right-hand side. So it's likely that our reaction sits more, so our positive half cell, so it's in favour of the copper rather than the copper 2 plus. So here's a final note on using standard cell notation to show what's happening in the cells without drawing everything. So the way we do this, you need to remember ROR, R-O-O-R. So if you remember to ROR, you'll get this right every time. It's reduction, oxidation, salt bridge, oxidation, reduction. So if we consider the first of these, I've got the standard hydrogen electrode as my left-hand cell, and my copper electrode as the right-hand cell. So for the standard hydrogen electrode, we would write the notation. So we've got the platinum, and then we've got a phase boundary. So I put a line. Hydrogen gas, phase boundary, and then a hydrogen ion. So I've gone from reduced to the most oxidized, and then we put our salt bridge, 2 lines, and we get the copper 2 plus, which is the most oxidized form in this half cell, and then we put a line for a phase boundary, and then we put copper with a solid as being the most reduced form. So it's ROR, R-O-O-R, reduced form, oxidized form, reduced form. And then if we have a look at this second cell, so I've gone for a zinc half cell. So I've got my reduced form is zinc metal, and that's in a solution of zinc 2 plus ions. So I put a phase boundary and then the zinc 2 plus and then the salt bridge. And then we have on the right hand side, we've got Fe3 plus is the most oxidized form. Fe2 plus is the most reduced form, and then we're using a carbon electrode, a solid carbon inert electrode. So again, it's raw, it's reduced to oxidized, oxidized version, the most reduced version, and then because we're using a different electrode, we put it right on the outside. So that's how we use standard cell notation. Now, the standard way of drawing these half cells and drawing the diagrams and of writing out the notation is that you put the negative electrode on the left hand side. So negative goes on the left and the positive electrode would go on the right. Now, you don't always know which is which, but you can find that out. And then what happens is the electrons move from the negative electrode to the positive electrode. Now, the only time we don't do this is if you're using and you're measuring against the primary standard, which is the standard hydrogen electrode. When doing that, the standard hydrogen electrode always goes on the left, so that you then can tell whether the cell that you're measuring against the standard is positive or negative, depending on where it sits next to the standard hydrogen electrode. Okay, that's all for today.